Good evening. So, this is a drawing that my daughter Mila made when she was in kindergarten. As you can see, she has drawn a very colorful Santa Claus, and you can also see that she tried to write her name Mila. But you can also see that she tried to, that she mirrored the letter L. Now, is that an early sign of later reading and writing difficulties called dyslexia? Or is there nothing to worry about? I will answer this question by telling you what is going on in the brain when we learn to read and what is different in children with dyslexia. So, for most of you, I think you agree that reading is very important in our society. You, as a university student, you read on average 15 hours a week. So it's really a way to get access to the knowledge, but also to communicate with friends. I'll show this with a small exercise that for most of you, this goes quite fluently. Try to name the color in which the words are written. If you try that, you will see it's quite difficult to say black, yellow, red. And that's because you automatically read what is written down, and this interferes with your answer. Now, for 7% of the people, this doesn't go so fluently, and they have what we call developmental dyslexia. That is a severe deficit in reading and or writing, and it's also a deficit that is persistent. So more concretely, you can assess reading and spelling abilities, and these children will score poorly, but also at multiple time points. And their level of reading and writing is not explained by their intelligence, the schooling they receive, or the motivation they have. Now, dyslexia in current clinical practice is diagnosed quite late, in grade 3 or even later. However, we know from reading intervention studies, so studies where you train intensively on reading skills, that the effects are bigger if you provide intervention earlier, already in grade 1 or even in kindergarten. And this is what we call the dyslexia paradox. Of course, if you want to provide an intervention earlier, we also need to be able to identify them earlier. And at the moment, we can make a rough prediction based on whether one of the parents has dyslexia, or you can do some tasks in kindergarten, such as assessing how many letters they know. But this is a very imprecise prediction. So the question is, can brain measures help us in providing a better prediction of who will develop dyslexia? Until quite recently, the brain was very more like a black box. We didn't know a lot about it. And that is because it's very challenging to acquire brain imaging data in young children. For those of you who had maybe already an MRI scan, you know that you have to lay still in a very confined space, and there's a lot of noise, so not ideal for a young child. Now, the past 10 to 15 years, a lot of efforts has been put in developing child-friendly protocols. So now we have finally insight in the young child's brain, and we can also see how the brain is changing through development. And this is very important, especially for reading. Why? Because our brain is not predestined for reading. When we're born, we don't have a brain that is made for reading. It's something that we have to do throughout development. Our brain has to reorganize. And I'll try to explain this a bit better by making the comparison with spoken language. So for spoken language, this is the result of an evolutionary process. So it's among us for more than 150,000 years. So across generations, our brain had the chance to adapt to spoken language. So when we're born, we have a brain that is genetically programmed to learn spoken language. And therefore, we learn it quite spontaneously, just by exposure. Now on the left, you see the brain of an adult who is listening to a sentence. And what you will see is that several regions are active, so you see them highlighted, and together they form the spoken language network. Now, importantly, if an infant is listening to a sentence, you will already see that spoken language network active. And this is different for reading, because reading, it's invented 6,000 years ago. So it means from an evolutionary point of view, it's too short to have a brain that has adapted across generation to this skill. So what we have to do is, during development, we have to rely on the plasticity of our brain. So our brain has to reorganize in response to the experience it has. And so this requires explicit instruction. So reading does not go as spontaneously as a spoken language. So if we now look again at the brain of an adult who is now reading a sentence, what you will see is that now the activation is starting more from the back of the brain. So it's more the visual network that is first active, and then it goes to the spoken language network. So when we learn to read and write, what you have to do, you have to reuse these existing networks, so the visual network and the spoken network, and you have to adapt them and reorganize in order to form a reading network. Now, I'll show you with a few examples that the brain of a child who cannot read is different from a child who can already read. So for the spoken language network, if you would ask a child in kindergarten, so before this child can read and write, what is the longest word? A snake or a caterpillar? The child will probably say snake because he thinks about the meaning and it's a long animal. And he's not so aware about these individual speech sounds in a word because there is no pause in between. So you really need someone like a teacher to draw the attention to these individual speech sounds. And so your spoken language network has to adjust from paying attention to the meaning to the sound structure. For the visual system, also some reorganization is taking place. Our brain is used, when you recognize an object, such as a cup, to ignore rotations of that object or whether this object is mirrored. So if, for the cup, the handle is on the left side or on the right side, it's still the same cup. But for reading, it suddenly matters. So if you have a B and you mirror this, this becomes a different letter. It's not the same anymore. And so also here, our visual network has to adjust. And so to come back to the drawing of my daughter Mila, this mirrored L, was this an early sign of dyslexia? No, it wasn't. It's just something very natural. It's a natural consequence of the fact that our brain still needs to reorganize if it's not yet reading. Now, all this reorganization, we can also see it in the structure of the brain. So here you see a simulation of brain cells that are communicating with each other. And what is important is that the more you use a certain route, the stronger it becomes. So by your experience, you can really shape the structure of the brain. Now we have MRI techniques to look at the structure. We cannot look at these individual brain cells, but at the larger scale, we can look at the structure, for example, of the brain regions. So the standard MRI scan that you see on the left, this can give information on the structure of the brain regions. We also have newer MRI techniques that allow also now to look at the connections of the brain. And so this way, we now have the tools to look at the structure of the brain across development. Now, is the brain in dyslexic in children, is that different? And when do these differences occur? So about 10 years ago, we started with our research team, the Dyslexia collaboration team of TEDxKULeuven, with a large project to investigate this. So we investigated the brain of children with dyslexia, already in kindergarten, and we also followed them up until the end of primary school. Because this way, we could see, are there differences? And do they only emerge throughout reading development? Because then they can be a consequence of a different reading experience. Because children with dyslexia, they often read less or in a different way. But if we find these differences already in kindergarten, then they can really be causing the later reading and writing difficulties. And then they can be used to predict who will develop dyslexia. So this is what we did. We had a look at the brain in kindergarten. And then of these same children, we had also reading and writing information across primary school. So we could see who of these children eventually developed dyslexia and who eventually developed typical reading skills. And then looking at the brain in kindergarten, we could see that the children with dyslexia already then had some differences in the brain. So there is a brain region that is very important for visually recognizing letters, and that was different in children with dyslexia, as well as the connection to the spoken language network. So to come back to the question, are these brain differences a cause or a consequence of the reading difficulties? They're not a consequence, because otherwise we wouldn't be able to see them before there is any reading experience. So they're really there from the very start. Now, we were wondering, okay, we see some brain differences, but do they remain present across development? Or can children with dyslexia catch up? Can they maybe, due to the extra reading interventions they receive, can they maybe catch up? So this is what we did. We had also information on the brain in grade 2 and also in grade 5. So we could see how the brain was changing during the first years of primary school, as well as during the later years of primary school. And so what we saw is that there was a very similar development in the children with dyslexia and the children with typical reading skills. For both groups, we saw that during this early reading stage, there was an increase both in the regions and in the connections. And in this later reading stage, there was more limited changes, so only in the connections, but not anymore in the regions. But what is very important is that because this development was similar in both groups, the initial brain differences in kindergarten, they remained present across development. So the children with dyslexia weren't able to catch up, although they received all reading intervention. But you have to know that these children, they received their intervention mainly in these later years of primary school, when there is less changes in the brain ongoing. So this might be too late to really influence the development of the reading network in the brain. So we wanted to see, what if we provide an intervention earlier? Could we then influence the development of the brain in children with dyslexia? So we did a study in kindergarten with children who were at risk for dyslexia. And then we let some of them play some games for reading. So every day they had to play some games. And what we saw is that the children who received this intervention, they had a larger development in both the brain regions and the connections than the children who didn't receive this intervention. So providing the intervention early gave us, then we saw that there was an influence on how the brain was developing, how this reading network of the brain was developing. Now, with all this information on the brain, can we now make an individual diagnosis based on an MRI scan? Can we put the child in kindergarten in the scanner and then look at the brain and predict whether this child will develop dyslexia? The answer is quite clear. It's a no, we cannot do that, because at the moment, these MRI measures of the brain, they're not precise enough to make a good prediction. What we can do at the moment is a better understanding of what is going on in the brain and what is different in dyslexia, so to inform general educational practices. Will it be possible in the future? Will we then be able to make a more individual prediction? Now big steps are being set to acquire large data sets. So with brain data of thousands of children. This is further facilitated by more child-friendly brain measures, measures that allow the child to move and that can measure activity during learning, so even in the classroom. And once we will have these big data sets, If we then combine it with AI-based prediction models, then we will have a better prediction, a more precise prediction of who will develop dyslexia and what the trajectory will be. But do we want this? Do we want to know the future? Because as Nietzsche said, the future influences the present just as much as the past. If I go back to the drawing of my daughter, this mirrored L was not an early sign of dyslexia. But what if a brain-based prediction model would have predicted that she would develop dyslexia? Would her kindergarten have been different? Maybe I would have put a lot of pressure on her to train very early to acquire reading skills because I know it's more effective. But that goes in at the cost of her having fun with friends. Gamification of early reading intervention can provide part of the solution, but not everything. And what if the prediction for a child is that this child will develop dyslexia, but he will respond very poorly to interventions? Would this child then, when he enters primary school, maybe not be motivated to learn to read, but then maybe become fully dependent on text-to-speech technology? Or would for this child be these new brain stimulation techniques, would that be an option? Because with these brain stimulation techniques, they're still under development, but what they do is that they stimulate the brain from the outside, specific parts of the brain, and then it can enhance your electric activity in the brain, but also potentially the learning ability. But we have to be very careful in children, because if you maybe stimulate parts of the reading network, maybe it goes at the cost of the development of other brain regions. And what if it becomes accessible not for the ones with a diagnosis, but for the ones who can afford it and want to acquire some kind of superhuman learning ability? So a lot of open questions. Technology is proceeding very fast. But now is the time to think together with people from industry, people from education, people from research about whether we want to implement these technologies and how do we want to implement them in order to give every child a fair chance to learn. Thank you.